here down at the plant at the Zulu Lithium project with the Chief Operating Officer of Stark Resources, Jaco Prinsloo. Thank you very much for taking the time. We're going to do a full walk of the plant in every last bit of detail. But we're right at the start, aren't we? And we can obviously see activity going on behind us and hear it. So tell me where we are right now and what we can see in the background.
So we're currently at the ROM pad. That's where they drop the material from the pit that's mined. And then from here they scoop it into the feed bin for the crushers.
Okay.
That scalps it off at 450 millimeters. That is then the feed to the primary crushing.
Okay, so the ore is coming up in dumper trucks from the pit. Large rocks behind us, as we can see, they're going into the crusher.
Yes, they fed in at 450 and then being crushed down for a suitable size to be fed into the secondary crushing unit. As you can see, the bars on top of the Grizzly feed bin, they spaced 450 millimeters apart, so that when rocks are fed in that's too big, they slide off and we can reduce them in size later, so that we don't block the crusher when it's fed.
Right, okay. And what is the driver of the wheel loader doing right now that we can see in the background? He's not actually feeding into the crusher at the moment?
No, he's just arranging the material to be ready, moving the bigger rocks to the side. And then once we're ready to start the plant, he will feed it in.
He'll feed it in. So he's taking the bigger rocks out that are too big to go in the crusher at the moment, and they will be made a little bit smaller?
Yes.
Okay. And then fed into the plant. That's the first start of the process.
Yes.
Getting it down to a bit of a smaller size.
Yep.
So then go through to get smaller and go through the plant.
That's correct.
Okay, excellent. Well, we're going to take a look at some more interesting parts of the plant.
Yeah, thank you.
Well, we've now come round, haven't we, to the other side, and this is the crushing area. So we talked about primary crushing, but this is also secondary as well. So let me know what we're seeing here.
Yeah. Okay, so the first unit at the back is the primary crusher. It's a jaw crusher. That reduces the material to go into the secondary crusher, which is a cone crusher.
Okay.
It's also a unit that circulates with a sizing screen. It's got a recirculating load to reduce it to the final sizes that we need.
Okay.
So we would need the -8 material to go to that belt going up there, and there on the other side is the -8 millimeter stockpile. Then it reduces to fraction 8 to 22 millimeters is what we need in the next stage, which is a sorting. XRT sorting, which is waste sorting.
Okay, so when you say cone crusher, what does that mean exactly? Can you describe what a cone crusher is?
The unit's it's called a cone because the internal is a cone. It's got liners, and then this cone moves in elliptical motion, and as the rocks go through, it crushes it.
Okay. And you're talking there about two different sizes of rock. So what you want to go through is 8 to 22 millimeters to continue down the plant. Less than 8 millimeters gets sent off.
Yes.
Is that just the optimal size that you want to go through the plant, that 8 to 25? Is that why you're aiming for that?
Yeah, so 8 to 22 is the ideal size to sort in this application.
Right.
So you want your top size to be not more than 3 times your bottom size.
Okay.
And that is what we see in the sorter. So it goes around liberation of the material so that you can see the minerals, and also then to have the 1-to-3 ratio within the sorting machine.
Okay, so 8 to 22 is the optimal size for the onward sorting?
I mean, that's what we chose during design phase. It will be tested and optimized further if need be.
Okay, so the less than 8 millimeter, that's just rocks that are just smaller than that. That does no good. It doesn't mean it's bad product. It's just not suitable to continue down the line.
So that we've got a reintroduction bin just pre of the mill that we can feed that material into, and then feed that straight into the milling circuit and then onto the flotation plant.
Okay, so you reintroduce it. So that goes into a pile, then gets reintroduced. So I can see obviously 3 conveyors. Yes, that's correct. Obviously one is the less than 8 mil, the other one is continuing down the line. What does this one do?
So this one is creating an opportunity to work on the rest of the plant while this section is running. So you've got your bin. When it overflows, it goes onto this conveyor, and then you can basically feed from this stockpile instead of from the crushers.
I see.
So if you want to do work on the crushers, you can feed from this stockpile directly into that feed bin while you're doing work on the crushers.
Okay, so it's if the hopper gets too full of material because the plant isn't perhaps running further down the line, you can keep crushing stuff, preparing, ready to introduce later.
Yeah, or if you want to do maintenance on the crushers while the rest of the plant's working, it creates a stockpile here and then feed it in while the crushers are offline.
Okay.
So as you can see, there's the belt magnet that catches any metal, anything metal that comes through. As they scoop up material from this bypass material into the bin, you might introduce some metal bolts, nuts, whatever, and that then sticks to the magnet, and the belt pulls it to the side and discharges into the bin.
Okay, yes, it's to stop any unwanted metals that have just been discarded or accidentally dropped going through the plant.
Yeah,
causing damage potentially.
That's to protect the downstream equipment.
Okay, well, we've covered all of the crushing, haven't we? The primary crushing.
Yes.
And now we're going to move on to the sorting.
Yes.
So tell me what we can see behind, because it starts with this green sort of hopper here, doesn't it?
That's correct. So we've got two sorting machines to cover the throughput that we need through this section. The feed is basically split into the two sections 50-50 through the chute feeding into those two bins. In a case where one of the sorters go offline, the feed is then building up in the one trouser leg of the chute, flows over to the other bin, and then 100% is fed to the one sorter.
Okay.
Obviously at a lower rate. So that creates a bit of redundancy. If a sorter goes down, we don't have the whole plant going down. And the purpose of the sorting XRT is to reject waste. So whatever is mined that is not ore is then ejected to the left-hand side, and only the actual ore that you want to be working with is going to the rest of the minerals.
Okay. So these two hoppers here are really to add redundancy, so you can keep running if one of the sorters goes down. Okay.
Yes.
And then tell me how the sorters work then, because this is what Stark are quite well known for, isn't it? Is this kind of sensor-based sorting?
Yes.
So tell me how that works.
You basically have an X-ray that goes through material and through the belt that the material is lying on. You need a monolayer of material, because at the end of the belt you're going to eject the particles that you want to eject by air jets. So as it flies over the belt, it times it from the time it detects what it wants to eject, and then it shoots out the particle by timing it. And below the belt you've got your X-ray sensor bar, which takes the image of the material. That image is then processed and fed back to the unit that says when you need to eject.
Okay. And what is the X-ray looking for? This is to get rid of what, lower grade stuff that's obviously lower grade, or what's going on?
You pick up the atomic number of the particles, and based on that you then eject. So it's basically looking at density. You pick up differences in density.
Okay.
So it's lighter and darker images. It's quite a clever imagery processing to then decide on what you're going to eject and what you're not going to eject.
And the stuff that gets ejected, is that no good at all?
Yes.
Right, so that just is waste material?
Yes.
Okay. Primary sorting, getting rid of the absolute waste,
yes.
And then we're going to secondary sorting as well to separate different levels of grade.
Yeah, secondary sorting is to upgrade the spodumene, which is then ideal for what you want going forward in the process.
Okay.
Yeah.
Okay, so we've talked about the primary sorting, the X-ray sorting.
Yes.
We've been up there. It's very difficult, obviously, to get in and get camera work in there. And there is a little window where it's too dark to actually see the blasting of the particles. But take us through actually what is happening in that X-ray machine and the sorter.
Yeah. So you would feed it in a back end of it, where it goes onto a belt. It's got a chute that slides down, so the material velocity or speed matches the belt, so that it settles quickly on the belt. You want the particle to stand still when you want to eject it, because you're basically timing its position from standstill and then shooting it when it flies over the belt. The chamber at the front where we look through the window is where the action happens, where you shoot out the particles, and that is lead lined because you're working with X-ray, so you need to shield it from coming out. The actual window we looked through is also lead window. It's got lead content, and it's basically got a splitter bar at where the material would normally go under the splitter bar as it flows, and if you want to eject it, you would just eject it over the splitter bar.
Okay.
And then you can see your chutes there. The back one is where it normally would fall, and the front one is where it's shot out.
Okay.
And materials then flowing through that chute and up onto the stockpile.
Yeah, so the stockpile here is the waste material,
Yes.
and then you've still got the two continuous lines going further down the plant. Okay.
So you can see the waste is darker in color than the product. But that might also be waste. If you look at the difference between that, that's quite, everything's light in color, and that's darker.
Nice. And with the blue, that's air compression, isn't it, for giving clean air to the...
Yes, you need clean and dry air. So we've got dry units there, and that basically feeds your air jets for ejecting the particles.
Yeah, okay. And the generators back there, there's quite a few of them.
Yeah, I think we've got 4 times 1.25 MVA. So, and that feeds the whole plant at the moment. There's no connection to any electrical grid at the moment.
Okay. Yeah. Can you just explain the tubular design of the conveyors? Because you mentioned earlier that's quite a significant design feature.
Yeah. So we took the lattice structure that you normally have for a conveyor, and we replaced the structural part of it with a tube or a pipe. The fabrication of that's just much quicker. Material-wise, it's roughly the same. Around tube or pipe is much stronger than a lattice. You've got much less welds, much less quality issues. The other part of the conveyor is that it folds in two. So you've got a flange in the middle where you put a hinge bracket on, and you then fold it in two. It fits onto a truck or even into a 12-meter container for shipment wherever you want it. When you get to site, you open it up. It's already fully commissioned at our facility. And it takes about 1 day to set up a conveyor. We normally would take your structure, your idler frames, your idlers, everything separate, and then only build it on site. But that saves a lot of time on site.
Does that also mean that if there's a problem with a conveyor, that you can replace it? Would it not be necessary to do that? Are they fairly straightforward?
Yeah, normally you'd replace parts on it. And we also do a galvanized structure, so it will last you 20, 30 years, even longer.
I like the idea of sort of the modular design, as you say.
Yeah.
You can ship it quite quickly, get it set up quite quickly. Does that also mean that the plant could, in theory, be expanded and added to when necessary?
Yeah, I mean, if you want to use a conveyor on a different function, you can quite easily do that. Sometimes you want to move a plant from place to place. You know, this front end section is where the conveyors are quite simple, so that you can move, get cranes, and within a period of 1 or 2 weeks, you can move this section to a different part of the site if you wanted to.
Okay.
Yeah.
So we've covered primary sorting in the X-ray, and the next part of the sorting, as I understand, is secondary sorting using UV light. Now, it's not here at the moment. This is something that will come later in order to upgrade the plant. Is that right?
So the UV sorting is really to upgrade the spodumene, split it from other minerals. And that will be installed where those orange tube feeders are at the moment. It's ready for shipment in South Africa within the next 2-3 weeks. And once it's installed, it will provide a higher grade to the rest of the plant.
Okay, yeah. So then in theory, the end product would be of a higher quality.
Either that, or you would increase your throughput.
Increase your throughput, yeah, okay.
Your
yield.
Production of your product.
Yeah, your yield.
Yes.
Yeah, okay.
Yeah.
So then after the secondary sorting, you've obviously got this other conveyor here that's taking material off with this big pile behind you. What is that?
So the next step is the feed bin to the mill circuit.
Feed to the mill, okay.
And when that bin overflows, it comes onto the stockpile. It also creates redundancy so that if your milling circuit is down, you can still run this section and not lose time.
Okay, and you've still got then ore building up.
Yes.
Yeah, okay.
So this stockpile can then be fed into the reintroduction bin where it goes back into the mill.
Okay, great. So we've completed all the sorting. The secondary sorting is coming later, as we said. We've moved on to the other side of the plant now, into the milling circuit.
Yes.
So what's the milling circuit all about?
So basically we take the material from the 8 to 22 millimeter that we sorted with, and then we grind it down to a size of 150, 200 micron in that range. So we are using the EDS mill, which is an impact mill. So basically it accelerates particles towards each other and then they break each other. So on a ball mill you've got two compressive forces from two sides, and that basically forces the particle to break. Where in this impact milling, you've got a point load on one end of the particle, and that causes the particle to break on the mineral boundaries, which exposes it much better for further liberation, or liberates it better for the flotation plant.
Okay. So it's important that it's milled. So it's milled down to almost as you might mill flour,
Yes.
for example.
Yes.
And that's what's needed. It needs to get to this certain size
Yes.
in order to go through to the next stage of
Yeah.
flotation
Yes.
and getting the spodumene.
Yeah. Yes, what you want is to get the particle liberated, which means enough of that mineral is exposed to attach to the bubbles within the float circuit.
The smaller and the more surface area it has, the better.
Well, you want, it can be bigger, but it needs to be liberated, so it needs to be separated from the other minerals.
Okay. Right, okay, so the smaller the better, effectively.
The smaller the better, but also if you grind too small, there's a range where it's too small and then it doesn't work either
Okay.
in the milling circuit.
Okay.
Also, you want to grind as coarse as you can to not waste energy.
Okay.
Breakage and milling is related to energy input into the particle to break it. And so you want to optimize to get to as big as possible size
Okay.
and work as efficiently as you can with the energy that you use.
And is the milling part of the optimization? Are you having to try and find the best sort of size?
Yes, we've got a design size that we need to comply to. I think in future operations they can optimize that and see if it makes sense to float at a bigger size. But
Okay.
at this stage we are aiming towards our design size.
Okay.
reduction.
Okay.
Yes.
So the mill is the blue that we can see there.
Correct. Yeah.
Yeah, it's pretty small.
Yeah.
Yeah, not a big footprint.
Yes.
Before we go further down the line, obviously there's this big grey container here, this Premier African Minerals and Stark. What's inside there?
So that's a motor control center. That's where all the cables get connected to, and where all the drives and motors on the site is fed from.
Okay.
Inside there you've got your VSDs, your soft starters, your buckets that would energize all the equipment.
Okay, and the circuit boards and the breakers and that
That's
kind of
correct,
thing.
yeah.
Yeah, okay.
So your feed from your generators goes in, and then it's split up into all the units
Okay.
via your circuit board.
Okay, right. So then after the milling,
Yes.
what comes next?
So part of the milling circuit is the sizing, the screening.
Screening,
So
okay.
you mill it, then you get a certain particle size distribution that then needs to be split up by the screen to say what goes to the next stage and what's been ground small enough to go on to the next stage, and what's bigger needs to be recirculated back to the mold to further reduce the size.
So that's why you call it a circuit,
Yes.
because it goes back through if it needs to get grinded again.
Yes,
Okay.
that's correct. Yeah.
Does the circuit add, is that pure reason for the circuit, or is there other advantages to having the circuit that help with production?
The circuit is there to reduce the material to the size that you need it.
Okay.
Yeah, that's correct.
So we're still in the milling circuit. We've moved down just a little bit so we can see more clearly the size screening. And next to that, you call it a cyclone. So what does this do?
So basically the sizing screens, we've got the first screen doing a coarse screening, and then after that the fine screen that does the final sizing. The undersize from that goes through the bottom screen comes to a MagSep roll, magnetic separation unit, takes out the magnetics, and the non-magnetics then flow the tank which is pumped through the cyclone unit. And that cyclone unit dewaters, and it also removes the minus 28 micron particles to deslime the material.
Okay, right, so there's a lot that's kind of happening there, I think, in a small area.
Yes.
But the first thing is the magnetics. So there's the magnet, and that's what's rolling. The unit turning on the blue
Yeah.
is magnetic, right? So there's magnetics within the milled material.
Yes, that's
What does that mean? What are magnetics?
Iron, those sorts of things.
Okay.
You take that out, and it basically sticks to the drum, and it's then scraped off
Okay,
and removed that way.
and that's potentially waste, potentially usable.
Yes,
Okay,
one of the two.
yeah, okay.
Correct.
And then the material it's going through, just explain that to me again. What exactly happens?
Yeah.
You say it dewaters.
Yeah, so during the screening process, we put a lot of water to be able to screen efficiently. Then it's pumped through the cyclone to remove that water, or some of that water, and also take the minus 28 micron fraction, the slime spit, the very fine fraction out of the feed.
Okay.
Because you don't want that to go into your float section.
Because if it's too fine, you'll end up getting a slurry or a sludge that will clog up the flotation. Okay.
Yeah.
So it's dewatering and removing any small stuff that's going to risk clogging up the machine.
So that minus 28 fraction with the water then goes to the clarifier, the water clarifier, which is then flocculant is put inside it, and you float or you flock out the slurry with a minus 28, and then you recover the water, which means you can use that same water as processed water to refeed to the plant.
Right, so it's a closed circuit in terms of water in that section.
Yes.
And then the minus 28 that's come out, no good? What happens to
No, that's
no good.
Just discarded.
Okay, and the rest of the stuff continues to flotation.
That's correct.
Okay, so we are now transitioning to the wet section of the plant before we get to flotation. We're stood on top of where those green cyclones were that we saw earlier.
Yes.
What is going on here? There's a few different tanks, lots of water moving around.
Yes. So the biggest one is the mica buffer tank, what you're looking at now. The one in the middle is the cyclone feed tank, and the bigger one on that side is the tailings tank.
The cyclone feed tank, that is the wet solution that's come off the screener that's now going to be fed into the cyclone for drying. Yeah. And then after that, that goes to...
Yeah, so it goes to the cyclone, it's dewatered, which means the overflow from the cyclone, it's got water, a lot of water, and then your minus 28 micron fraction. And the rest is underflow, which goes into the mica buffer tank.
Okay, overflow and underflow. So let's start with overflow. That's obviously water that's overflowing.
Yeah. Okay, so the overflow is the lighter particles, like the minus 28.
Yeah.
And it's because all the particles are sort of the same density, but because of their small size, they go to the top. Yeah. They're lighter than minus 28 microns. And the bigger particles, the plus 28, then flows to the bottom and goes to the mica buffer tank, ready to go to mica flotation. Okay,
and the lighter that goes over the top, that is going then to...
It goes to the clarifier, where you then recover your processed water, and whatever settles out in the clarifier is then also pumped to tailings.
That goes to tailings, okay, so the clarifier is recovering your water?
Yes.
Okay, and then it's no good, that material. Okay, that makes sense. So mica, where's the spodumene fit into this part of the process?
So the stream going from here to the float section contains mica and spodumene.
Right, okay.
And the first mica float section is to take out the mica and then float it further and take the spodumene out.
Okay, yeah, okay. So the heavy material sinks to the bottom, then goes to mica float, but that's mica and spodumene, and mica is taken out first before the float for the spodumene.
That's correct.
Well, I'm here now with Tineke du Plessis, the Junior Process Engineer for Stark, here at the Reagent plant. So thank you very much for joining me.
It's a pleasure.
This is the Reagent section of the entire plant.
Yes.
It's very interesting. It's also quite complex, I think, isn't it?
Yeah.
There's different sections to it. So could you just take me through each section, and then we'll see what we can learn?
Yeah, with pleasure. Will do. Okay. So firstly, we have the sulfuric acid plant. This one is the simplest but also the scariest of the 4 plants. We have IBC, so an IBC containing sulfuric acid is placed on top of this tank. From where on the other side, I'll show you now, there's a valve that connects the IBC with a hose into this bottom tank.
Okay.
So there's also a levered sensor just to show you when it's empty or when not, and when you should replace the IBC.
Okay.
So this one is simple in the sense that there's no makeup, so it's not like you're adding water or more than one reagent. It's just the IBC going into the tank, flowing through the pumps into the reagent, into the plant.
And when you say it's dangerous, it's because it's sulfuric acid?
It's sulfuric acid,
Okay, and that's dangerous in itself.
Yes.
What's the sulfuric acid used for?
In this case, in this plant, it's used as a pH modifier for the mica plant. So mica floats at a pH around 2.5. pH is very important for flotation. So it's important to maintain this specific pH to selectively float the mineral you want to float.
Okay, in this case mica. So it's a pH modifier to get to 2 to 2.5 pH, which is what mica needs to float at.
Yes.
Okay, so that's that section complete, is it?
Yeah, it's
okay.
as simple as that.
Right, well let's
Basically
look
just important to wear PPE here.
Of course, yeah.
Okay, this one is actually, I didn't count it as part of before. This is the lime plant.
Lime plant, yep.
Yes, so this is used to neutralize the tailings. So before we pump to the tailings facility, we make up lime here, which is then pumped to the tailings tank. So basically very simple as well. You have a lime hopper, which is just here at the front with a screw feeder. And an alarm sounds when the hopper is starting to get empty. You just grab a bag, you rip it open, throw it in there.
Okay.
Water is being added there with a flow controller just to make sure the water to lime is correct. And then it's just pumped there based on the pH reading.
Okay, and that's for neutralizing the tailings, to make it, safe to go out into the environment?
Yes, so we neutralize to a pH of 7. So due to the low pH of mica, the pH of the tailings tend to be acidic. So that's why we are neutralizing with a base, and we don't really have an acid neutralization because the tailings really aren't ever higher than 7.5.
Okay.
Yeah.
Okay.
Yes.
Thank you. Excellent. So let's go to the next part of this exciting part of the plant.
Okay, this is Flotation EDA. So
okay.
This is a collector for mica flotation. So for the flotation, both flotation plants, we have a pH modifier and we have a collector. So we had the sulfuric acid as the pH modifier for mica, and now we have the Flotation as the collector, the mica collector. So yeah, basically this tank is actually 2 tanks divided. Okay, so this is a batch process. So you make up a batch, then it's transferred to the dosing tank. So the mixing tank, you make it up and it's transferred to the dosing tank. Okay, so first you open, there's a latch there at the top. So that's the latch to the mixing tank.
Okay.
So you open that, you pour in your EDA drums and water, which is also monitored by a flow meter. Then you can close it, and then when the batch is completely mixed, it's automatically transferred by a transfer pump into just next to it. It's just a divider in the center of this long. It's similar to that. There's just a divider there. Then it's just transferred into the dosing tank.
Okay.
Okay, or the storage tank. So from there it's dosed, and then when the batch is already transferred, you can start making up your next batch to make sure you never run dry.
Okay, so it's making up a batch.
Yes.
Okay, and then it's stored until it's needed in the flotation plant. EDA, what is that?
That's just a mixture of organics and frothers and typical flotation reagents to be able to float the mica.
So these are reagents to enable to float the mica.
Yes, that's exactly what it is. Yeah, so it just enhances the hydrophobicity to allow it to float and suppress the rest to sink down.
Okay, so why is that important then?
So that's once again more important in terms of the pH to make sure it's mica specifically that is floated.
Yeah.
So if we dose this now, then it will make sure that mica floats at that pH. However, if you overdose on the collector, other elements that might be waste, or in this case, it's a reverse flotation. So in this case, we're floating off the mica first, then the tailings goes to spodumene flotation. So that contains the spodumene. So if we overdose here, we might have some spodumene floating at mica, which is not what we want. We want it to float at spodumene.
Okay.
So you don't want to overdose, because then you might have other parts or other elements that you don't want to float that will float.
Okay.
And if you dose too little, then your mica won't necessarily float fully. Yeah.
And is this a process that you're fine-tuning, or?
Yes, I think that is basically what's going to happen with commissioning. We're just going to take samples and then we'll take it from there. Basically, the current values are based off of test work. Okay,
but the main idea is to float mica. And is that just science? Is that just physics that causes it to float?
Yeah, flotation in my mind is a little bit of black magic, but it's basically the flotation reagent. It links, it it binds based on the surface properties of the different particles.
Okay.
So then it will bind to certain particles rather than others, and then increase the hydrophobicity, which will just allow it to float to the top, because it then doesn't want to really mix with the water.
That's what George was explaining earlier. You want to make it hydrophobic so that it's attracted more to the bubbles, and then it goes to the top.
That's why we add the air.
You add the air, and that's what causes the bubbles.
Exactly.
Okay.
That's perfect.
Fantastic. Thank you. So move on to the next tank. Is this the mixing tank for the spodumene then, or?
This is sodium hydroxide.
This is sodium hydroxide.
Yes.
Okay.
So yes, spodumene pH modifier in this case.
Spodumene pH modifier.
Yes.
Yep.
So this works exactly the same as the EDA plant, in the sense that you have a mixing tank and you have a storage tank or a dosing tank that are adjacent to each other. So there's just a divider on the inside. So on this side, you just have this latch that you open where you put the bags in. There's like this claws that grabs the bag, and then you just cut it open and you close it. And when you open, the bag stays behind. So then you can just remove the bag. So first you start the sequence. It fills up until a certain level with water. Then you add then you need to add your reagent, like the dry sodium hydroxide flakes. And then it continues adding water until a certain level is met. Then if the dosing tank is empty enough, then the batch that you made up in the mixing tank will transfer, so that you always have sodium hydroxide available.
Okay.
So, then you can make up your next batch.
And this will then go for the spodumene flow.
Yes.
And it works in the same way.
Yes, we want a pH of preferably 10, but between 8 and 10.5 will probably be fine.
Okay. Perfect. Thank you.
Yes.
So the last part of this section then, what can you tell me about this piece of equipment?
Okay, so this is, in my opinion, the second scariest part of this plant.
Okay.
So this is the collector plant for spodumene. This collector is the LR19 collector.
Okay.
So this is now a bit more complex than the other three, because we have 4 reagents that are added here.
Okay.
Okay. So here we have 4 pumps that will pump the different reagents, and the 4 pipes, which you then add into either a drum or an IBC, or whatever the vessel is the respective reagents are delivered. So here you pump in fatty acid, kerosene, Aero 801 and MIBC frother.
Okay.
Once again, based on test work, this is the reagent that best allows for spodumene specifically to float at a pH of around 10, which we use the sodium hydroxide for. Because obviously we come from the mica plant where we have a pH of 2, then we need to increase it to a pH of 10. So how this works is you have a makeup tank and you have a storage tank, but this time they're separate from each other. Main reason for that is it's a very sticky, highly viscous material. So we need that conical bottom at the storage tank to be able to just transfer into that one successfully. So basically it runs in sequence, 1 reagent at a time will pump into the makeup tank. There's an agitator there as well, which will just make sure everything is nicely mixed. And as soon as everything is nicely mixed and the dosing tank is empty enough, it will transfer into the dosing tank.
Okay.
Yes. Once again, then you can make up your next batch to be ready for when your dosing tank is empty again.
Okay.
In this case, the reason why this is again kind of scary is because it's highly flammable. So we have flame arrestors and a seal pot and everything to make sure that this plant is as safe as possible.
Okay.
Yes. And obviously all the pumps are IX rated and everything.
Okay. So effectively you've got pH modifier collector for mica, and then pH modifier collector for spodumene.
Yes, exactly.
So they both go to the different flotation plants, and they're both responsible for the overall collection of the mica or the spodumene.
Yes, exactly.
Yeah. Okay.
So the collector ensures that the particles become hydrophobic, and the pH just ensures that selectively what you want to float will float. So other stuff can float with the specific collector at different pHs. So that's why we need to specify both the collection and the pH. Yes.
Perfect. Well, thank you very much for taking us through that.
That's a pleasure. Thank you, Mark.
So just next to the reagent section of the plant, there is the control center, isn't there, in that grey container. So really, what goes on here? Obviously, the controlling of the whole plant.
Yes. Yeah, that's where you control your whole plant from start and stop. You've got your start sequence, which will start things from the back of the plant to the front before you feed material. You also control levels on tanks. When it reaches a high level, the pump switches on. A low level, the pump switches off, as an example. We basically have a programmable logic control system connected to a SCADA, which is your interface that you deal with, where you can see physically there's a conveyor, press on the conveyor, start the conveyor, stop the conveyor, and then you have your overall plant start-stop functions. And you can also start per area, basically program whatever you want in terms of controlling the plant. So it's a fully automated plant, and the control operator basically controls everything that's going on. So you have your shift supervisor in the field, the metallurgist running the plant, radioing in, please start this section of the plant. They reset everything, make sure it's healthy, start it, and then there's confirmation whether it has started or not.
Okay.
Also very important when you shut down the plant, so that your flush sequence is started and everything is then stopped in the right order, so that you don't get blocks and spillages of things overflowing.
And the idea of the plant is to run 24/7, is that correct?
Yes, your float section needs to settle down and needs constant feed. So you have to run a shift system where there's a handover with the plant running, and then you have planned shutdowns for maintenance.
Planned shutdowns for maintenance. How long would a maintenance period last? Or does it just depend on?
Depends on what tasks you need to do in that maintenance shut. But you've got a few days, maybe a week, a month or so, a week per month. The plant was designed to run 22 days per month, which leaves quite a bit of space. If you're very efficient in maintaining it, you can actually operate more than that. But you will get to your product throughput in 22 days, 24-hour shifts.
Okay, yes. So you'll get the product throughput that it's agreed when the designs were set up in
That's
that 22 days. Okay.
Yes.
Well, thank you very much. We'll go and have a look at the flotation section now.
Okay, thank you very much.
So, coming from the reagent dosage, we are now looking at, or behind us, is the mica float. Is that correct?
That's correct, yes.
Okay. So tell me, it looks very complicated. There's lots of tanks and pipes around the place.
Yes.
But can you explain the process?
So basically, coming from the mica buffer tank, that's where we ended up on that side, into the tank on this side, where it's the material is diluted, or the slurry is diluted to a point where it's ideal for mica floating. You then add reagents to the float cell, the rougher float cell, and then your mica is floated, basically attaches to the bubbles and floats over. Then you've got a scavenger cell to the right of it that basically gives it another go at floating the mica before the tailings material then goes out to tailings.
Okay. So it comes in from the mica buffer. It's diluted with water.
Yes.
Okay. You add the reagents.
Yes.
And that's what causes the bubbles.
Yeah. You agitate it. You put aerate it with air, and then with reagents, all of that together makes bubbles.
Okay. And the first tank it goes into is the rougher.
Yes.
Which is doing what?
The rougher is basically the first go at floating the mica.
Okay.
So it's agitated, and then the mica attaches to the bubbles, which then flows over to the outer portion of the float cell, and that's then fed down to the product filter press.
Fed down to the product filter press. So that's the first go. Okay. And you mentioned the scavenger.
Yes. So the scavenger takes the underflow from the rougher cell, and then there's another go at floating the mica, and whatever you float there also goes to the product tank, the mica product tank, which then goes to the filter press.
Okay, and then the tailings is taken away, put in the tailings storage facility, as it's known. Okay, right. So we've covered the mica float, and behind us now is the spodumene float. This is the more exciting part, certainly for investors anyway. This is where the spodumene is then made to go out to market.
That's correct.
So it's a similar process, isn't it? You've got the rougher and you've got the scavenger, but there's a bit more to this. So take me through the process here.
Okay, you start off with your rougher. The froth then flows over the rougher and is then pumped from the top, goes down and is pumped to the next float cell, which is a cleaner number one. And that's where you basically float the spodumene a second time, and then anything that maybe shouldn't have floated the first time is then released. That can be repeated 2 more times, so we've got quite a nice flexible setup. We've got 3 cleaner stages. We can see at the end of the day whether we need 3. We might get away with 1 or 2, and then see if we want to use the second, third one to get to a cleaner product than what we actually need.
But the idea really is to get as cleaner or as pure, another word you can use?
That's correct, yeah.
Get as pure as possible.
Yeah.
That the customer wants, really. And it might involve using all 3, or it might involve using 1. Okay.
Yeah.
But it shouldn't need more than 3, generally speaking?
No.
No, okay. And the process is the same. It goes into the tank, the reagents are added, it's agitated,
yes.
The froth is created that then binds to the spodumene,
yes.
and then that's taken off
That's correct,
the top.
yes.
Okay.
Yeah, from there it goes to the filter press tank, and it's filtered. In the filter presses it's compressed, thrown down as a cake and into a bulk bag for shipment.
And then the same thing with the tailings, that's taken off and goes off to the tailings storage facility.
That's correct, yes. So it goes to the bottom of each float unit. Gravity feeds through all the units back out to the bottom, goes to a pH correction tank, and from there out to the tailings.
Okay.
That's correct.
And that's the end of the process. We then finish with the final product, all being well, in the filter press.
That's correct.
Okay, so we're here finally at the end of the plant, at the end of the process. This is where the end product would roll off the line, so to speak, go into bags, and the trucks would then come and take it away. I can see a little storage facility there. Presumably that's where the bags will go when it's all ready. But just explain to me, we obviously covered the flotation and the solution coming through. How is it then pressed into this cake that you talked about before?
Okay, so you basically pump the material into the filter press, and then you squeeze it with a hydraulic press. Then you blow air in between to compress the material and squeeze out the water. Then the plates are released from each other, pulled away from each other, and then the cake is exposed, falls onto a screw feeder, which also breaks it up, to then screw it out and into the bagging plant.
Okay, and the water that's run off then goes back?
Yes. Goes back to a tank, which is then pumped to the tailings tank and then pumped back.
Okay. So really, in simple terms, the solution is pushed through, goes between plates. That's then, all those plates are then pushed together by a hydraulic press, squeezing the water out.
Yes.
For 10 minutes, as you said before. Plates then open, the cake drops
onto a screw feeder,
and then goes into the bag. Okay.
Yeah.
And you also have a bit of an analogy, don't you, or some words to remember this process. Just tell me what that is.
Yeah. So you pump, squeeze, blow, and then the cake falls on the screw and you screw it into the bag.
Okay, fantastic. You pump, squeeze, blow, the cake falls onto the screw, and then you screw it into the bag.
That's correct.
Fantastic. Well, thank you so much, Jaco, for your time today, taking me through this plant. We'll leave it there. I hope that covers everything in as much detail as everyone wants. But thank you so much for your time today. It's been an absolute pleasure going through this with you.
Thank you, Mark. Thanks for the opportunity.